Suppose x is a geometric random variable such that x is the number of trials until a success given an arbitrary situation. Then the expected number of trials until success is just 1 over the probability of the success. Why is that? That's a pretty cool trick, and I'll show you. So given x is a geometric random variable, obviously there's not a fixed number of trials, and we're trying to find the trials until success. That's usually the key word for uh, finding a geometric random variable. In our case, suppose that the arbitrary success happens on the kth trial. Now what is the probability of this? This is the probability that that the number of trials until success is k. Okay, because this is when we succeed, so the number of trials is when we succeed. Pretty intuitive. But what is this probability? It is, as we've seen, the number of failures, so 1 minus p to the k minus 1 times p. And to sort of break this down, here I'll actually write it in yellow because I wrote it in yellow before. P is our probability success. And 1 minus p is the probability of failure. And this makes sense because the total probability needs to add up to 1, and so obviously 1 minus p plus p is just 1. Okay, and the reason why we have the uh, the, the exponent as k minus 1, well, if we succeed on the kth trial, then these are all the trials before k. On the kth trial, the last trial, we succeed, so we times it by p. So it's all the failures times the success probability. Okay, we found the probability, but we need the expected number of trials. How do we get to that? Well, we can rewrite this to find the expected number of trials as the sum of all the terms, or all the trials, times the probability, right? Using linearity of expectation. And we can factor out the p. So we get k times 1 minus p to the k minus 1. But now how do we deal with this? Because we know k, there's a formula for that, but how do we find the sum of 1 minus p? Well, let me show you if I can figure out my colors here. There's a cool series trick we can use to find this. I'll write it in a different color. And so, given a sum, let's say so this is 1, given a sum of k times r to the k minus 1, this actually equals 1 minus r squared. Actually, I believe this is the rth term starting from r. Yes, I believe so. And so we can use this by just replacing r with our 1 minus p. And so knowing what we did here, we can say, actually we don't need to write the sum because we're evaluating it, which is just, so everywhere we see an r, we replace it by 1 minus p, so 1 minus p squared, which is just p times, this becomes just p, so it'd be p squared, which you can cancel out 1 p, and that becomes 1 over p, which is exactly what we were trying to prove. And this whole idea is super useful. So given a probability question, you don't have to write out the sum each time and evaluate it. You just know this pre-proven trick, corollary. I don't know what you would call it in math terms, but it saves a lot of time. And just to show how useful it is, let's just do a random example. So let's say you have a deck of cards. And this is a normal deck of cards of 52. And you're trying to find the expected number of trials until you get a king. Any king, any suit king. Until a king. And once again, usually whenever you see until, you're dealing with a geometric random variable, which means you can use this trick at any time. And so we know that our expected number of trials, well, first let's find the probability, but that's the easiest part, right? So the probability of x, or probability of a king rather, is, well, think about it. There's 4 kings in a deck of 52. So big whoop, it's 4 over 52. So it's 1 on 13. Then the expected number of trials is 1 over 1 on 13, or 13 trials.